Hello students, this video is designed to help you work with the problem sets from Unit 10, the first 4 specifically. We're talking about circles, talking about different lines within circles, angles within circles, arcs within circles. We're just crazy about these things. Anyway, take a look at the Lesson 1 problem set. You should have tried this before. If you haven't already done so, please pause the video, try this out, and I will show you the correct answers in a few moments. Alright, these first several problems we're all talking about two different kinds of angles. Inscribed angles, which are angles with the vertex on the edge of the circle, and central angles with the vertex in the center of the circle. In every case, we were able to figure out the different arcs that were intercepted. For example, in this case, this arc that was intercepted is 140, and this angle is 70, because an inscribed angle is half its intercepted arc. Some of the problems used this idea, the 360 idea, which means all of the arcs added together in a circle are equal to 360. So for example, here we knew this arc was half the circle, so that's 180. This arc was 140, and this arc had to be 40. In this one, this arc was 260 ABC, so that meant this arc had to be 100. So we were using that trick to figure out the missing arcs. In this case, we knew that any inscribed angle is going to be half of the central angle that intercepts that same arc, because this arc is twice as big. Is twice as big as the inscribed angle, and is exactly the same size as the central angle. No surprises here. You should have been able to get through these pretty effectively. All right, take a look at the next page. These were short answer questions, not multiple choice. So try them out, pause the video, and then come back and see if you're right. Alright, in question 6, it tells you that the arc NK is 130 degrees, that's this arc, and it then tells you that the arcs are congruent. Well, if this arc is congruent to this arc, then this is 130 and this is 130, which means 360 taking 130 away twice, that gives us 100. That means this arc is 100, because all the arcs have to add up to 360. That means this is 50, which is our final answer. That angle is 50 degrees. In this one, we were using the same kind of idea. 86 degrees was given to us, which means this arc is twice that, 172. 172 taken away from 360 is 188, and then 94 is half of 188. For number 8, the correct answer was statement 2, that these two triangles are similar. How do we know they're similar? Well, I see angle A here and angle B here. They both open up onto the same arc. They both open up to arc CD. See how this arc, let me outline it for you here. See how this arc CD has this angle that's intercepting it, CAD, and it's also got this same exact arc being intercepted by this angle, that's CBD. Both of these have the same exact intercepted arc, so they must be the same exact measure. Same thing with these two, and then these two angles were vertical angles, so they are congruent to each other. So angle, angle, angle. That doesn't prove triangles are congruent, but it sure proves triangles are similar. And then for question number 9, solve for the value of each variable. It was the same kind of deal. This arc is 80, this angle is 40, and this angle is also 40 because it's the same intercepted arc. These two angles are vertical, so I use triangle sum theorem to find x. And then in this case, inscribed angle 20, arc 40. Inscribed angle 27, arc 54. And then this arc here, this angle, as a matter of fact, this angle x is just 40 plus 54. A central angle is going to be equal to the arcs it intercepts. All right, moving on to problem set for lesson 2. Pause the video, try it out, and see if you got it right. For most of these problems, you were dealing with the idea that two parallel chords are going to be making two congruent arcs. So in these first two problems, parallel chords, congruent arcs. In this case, same thing, parallel chords make two congruent arcs. We don't know what the measure of these arcs are, but we know that they're the same, so we can set up an equation. 106 plus 24, those are two of the arcs of the circle, plus x, those are the other two arcs of the circle. That should be equal to 360, and then solve that equation. Little algebra review for you. For the fourth one, same idea, these two arcs are the same as each other, so if this one's 30, this must be 30. If AB is a diameter, that means this arc, this purple arc here, is going to be 180. So adding them all together and subtracting that from 360 gets you 120. So this arc up here is going to be 120. And then for number 5, this was a little bit of a preview of the next couple of lessons. This is our two chords theorem, which is piece times piece equals piece times piece. We know that this piece and this piece are both 15 because when a radius is perpendicular to a chord or a diameter is perpendicular to a chord, that means the chord is bisected, so this part is 15, this part is 15. The entire length here is 34, which means this piece is going to be x, and this piece is going to be, well, 34 minus x. That's where this 34 minus x comes from. Multiplying them together gives us another algebra review problem, a quadratic equation which has two answers, 9 and 25. It tells us that BE is smaller than DE, so BE is the smaller of the two. It's got to be 9. All right, moving on to the next page. Try this by yourself, and then unpause the video, or I guess press play on the video, and see if you're right. All right, yet again here we're given a problem in which we have two chords. This piece is 17, FB is equal to 17, and that's a radius, which means this part AF is also a radius. And it's given to us that this piece is 2, which means this piece must be 15. Adding 17 and 15 gives us 32, so that means this piece of the two chord intersection is going to be 32. This piece is 2, as already given, and we know that when a radius is perpendicular to a chord, it splits the chord into two equal parts. It bisects the chord. So I solve this equation, this very simple algebra problem, and I get 8. For this one, it's given to us that the radius here is, the radius here is perpendicular to this chord, which means that it splits the chord into two equal parts. In other words, SL and TL are going to be congruent to each other. I also see that RS and D are both radii, which is a plural of radius, which means they're always going to be congruent to each other. In a circle, all the radii are congruent to each other. However, RL and LE, we don't know anything about them, so I don't know. And LOL, I'm not really sure what that stands for. For number 8, it gives us that these two lines are perpendicular to each other. It also gives us a bunch of other information, but the important information at the beginning here is that this piece is y plus 10, FC, and then the whole chord is 4y minus 20. Well, I know that this piece times 2 should be equal to the whole entire chord because these two pieces are equivalent to each other, congruent. So I solve that equation to get y equals 20. I substitute in 20 to get df. The measure of df is going to be equal to 30, which means that this is equal to 30, which means the whole thing is equal to 60. And then finally, I'm asked to find OA, which is the radius of the circle. And you can see this right triangle that's drawn here. So the right triangle has a piece here, which is 16. That's one of the legs. This leg is 30. And this hypotenuse is 34. For question number 9, it tells us that the radius is 5, which means this part is 5, this part is 5, this part is 5, and this part is also 5. The piece up here is 2, which means this is 3. And it asks us for the length of BD, which is this whole entire chord. Well, first I'm going to find this part, which is the side of a right triangle. It's a 3, 4, 5 right triangle, but if you didn't remember that, you could have used the Pythagorean theorem. So this part is 4, ED is 4, which means BD is equal to 8. It's twice as long. All right, moving on to the lesson 3 problem set. Pause the video, try these out, and then see if you did them right. All right, as we spoke about in class, the formulas that were on this lesson, you do have to memorize. So most of the problems here that I labeled with, for example, 2 secants or tangent secant, all these labels are indicative of what formula I'm using. So if you're trying to figure out what those formulas are, refer back to lesson 3. Anyway, in this one, it told us the arc here, and it told us that central angle. Well, let's be careful here. It wasn't a central angle because it didn't come from the center. It is an angle that is formed by two chords, though. So that angle is equal to far arc plus near arc divided by 2, and the lucky thing is that it doesn't really matter which one is the far and which one is the near, as long as you add them all together and divide it by 2. So if this is 64, this is x, and this is 52, so we substitute into the formula, and we solve for x. Over here we have 2 secants, which is far minus near over 2, so 2 chords, far plus near, 2 secants, far minus near. We solve it out the same exact way. For number 3, it gave us a central angle, which was 108 degrees. That means that this arc is 108 degrees, and that gave us enough information to solve for this angle. This is an inscribed angle. It doesn't really look like an inscribed angle that we saw in lesson 1, but it is inscribed because the vertex is on the edge of the circle, which means if this arc is 108 degrees, this must be half of that, which is 54 degrees. And then last but not least, it gave us a ratio. Ratio problems are solved like this. 3 to 4 to 5 means 3x, 4x, and 5x. So we label the circle. We know that all of those arcs together equal 360 degrees, so we solved for x. We substituted that value of x into each of these measures to get our arcs, and then we did far minus near over 2. Now keep in mind the tangent secant rule is the same as the 2 secants rule. It's far minus near over 2, far minus near over 2. So no big deal on that. Next page is using more of those formulas from lesson 3. So pause the video, try them out, and see if you get them right. All right, this page was mostly about looking at line segments inside of circles. And if you remember from the previous page, it was mostly talking about angles and arcs. We're still using that formula sheet from lesson 3, though. In this case, it was 2 chords, piece times piece equals piece times piece. In this case, it was a tangent secant, which means part times whole equals tangent squared. And please remember that the part in the formula means the outside part. It's referring to this part, which is 16, not just the smallest part. It's always going to be the outside part. So it's just basically taking these different formulas for 2 secant, that's part times whole equals part times whole, substituting numbers into them, and then solving them for x. This is a little bit of an algebra review, but you should be good at algebra because you're in geometry now. Again, this is 2 chords, which is piece times piece equals piece times piece, and simplest radical form meant we had to take the square root of 72 and simplify it. All right, moving on to the next page. This is actually the lesson 4 problem set, the last problem set that I'm going to be going over. Pause the video, try these questions, and then come back to see if you get them right. The main idea for this lesson 4 problem set was that a radius and a tangent intersect at a right angle. We later talked about how tangents intersect a circle, and if they are coming from the same point, then they're congruent to each other. Anyway, in this case, we're using our Pythagorean theorem because as soon as you see a right angle and it's a right triangle, you should think Pythagorean theorem to find the missing side. You may also use trigonometry, but that's in a little bit more of a rare case. In this case, we actually had to draw a picture. It says circle O, which means O is at the center of the circle. Point A is the point of tangency, so it's on the circle. And line segment AB is the tangent, so it's outside the circle. So all of these words helped us identify where to draw them. And of course, as soon as you draw that triangle, you should see that it's a radius and tangent meeting together. Radius tangent means right angle. For number 3, this was a little bit of an algebra exercise, but you should remember how to double distribute because you're good at algebra. 4 times 4, 4 times r, etc. And this simplified nicely because these r squareds eliminated each other. We subtracted r squared from both sides and we got rid of them. The end of the story is that r is equal to 16. And then for number 4, we're using, yet again, Pythagoras' theorem. What would we do without him? All right, last page of the document. This is the last page of problem set for lesson 4. Pause the video, see if you can do it, and then come back and check your answers. All right, there were a lot of questions in class on these, so I want to make sure I answer them pretty thoroughly. It says an angle inscribed in a semicircle is a right angle. And it gives us all this information about all the lines in this circle. There's a lot of lines, but one thing you have to focus on is this. An angle inscribed in a semicircle is a right angle. Well, that's always true, because if it's a semicircle, that means half of a circle. That means an inscribed angle for a semicircle, half a circle, 180 degrees, is going to be equal to 90 degrees, because inscribed angles are half of the intercepted arc. So this one is the only angle that is intersecting a 180 degree arc. This angle down here, it doesn't make it. It gets only from C to B, and that's not a semicircle. The semicircle would be from D to B because DB is the only diameter drawn in this circle. Everything else is just not an inscribed angle that intersects a semicircle. And then for number 8, we had to go through each one individually and disprove them or prove them. ABC and ACD, as you can see in blue, they're both right angles. This is a semicircle intersected by an inscribed angle, and this is a radius and a tangent together, so they're both right angles. BAC and DCB are both intersecting this arc, this green arc, so that means they both must be equivalent. And then CBA and AEC are also both right angles, so those must be congruent as well. So the only one that is not always true is ACB and BCD. All right, that is the video on the Unit 10 problem sets from lesson 1 through 4. Good luck studying.